In part one, I introduced a scenario where when a person walked from his home to his workplace in a straight line, not turning right or left, just straight. I explained the difference between displacement and distance. And after that, I introduced how to interpret the displacement graph when it's plotted over time. If you cannot tell what flat line means, what this slope means, what is the direction of the slope means, and what is the sharpness of the slope or the curve versus straight line, I want you to watch part one. So in this video, I'm going to introduce two different concepts in physics, which are speed and velocity. Speed is the number quantifies how fast something or someone is moving, right? So in this case, speed only gives you the sense of magnitude. Therefore, it is a scalar. On the other hand, velocity is a very similar concept in that the number of velocity gives you how fast the person is moving, but at the same time, it gives you the direction of the person moving. And therefore, it gives you the magnitude and direction. It's called a vector. The mathematical formula to obtain a velocity is delta d divided by delta t, which is the final displacement minus the initial displacement divided by the final time minus initial time. I recreated the exact same figure using the actual data. So what you see on the first two columns is that you see the time of every 10 minutes and then position of the first 10 minutes not moving, and then at the constant pace, the person began to walk to his workplace for 5 miles, covering 1 mile every 10 minutes, and getting to his workplace at the 5 mile point and stay there. In the third column, so this one is over here. So when you take a look at the formula, it's simply final minus initial. Next, final minus initial. On the next column over here, I did the exact same final time minus initial time and all the way down. Therefore, what I obtained was the denominator of the displacement. So all I needed to do was I divided this number by this and I obtained velocity. And the plot of this column is shown over here. By definition, velocity is change in displacement. When we look at the first two data points, there's no change in displacement. So there's no motion, right? So therefore, zero displacement indicating zero velocity. That's why you see zero over here. It's important to understand that when there is no motion or no displacement, there is no velocity. And we shift our focus to the next 2 points. Velocity is a change value, right? So we always compare two different points. So there is a change in velocity from 0 to a certain value, right? So that's why you see a positive value of velocity over here. And y is going up instead of going down is because the position changed in the positive direction. Another interesting thing you can see is now you see a flat line. When we learn displacement, when we saw flat line, it is zero, meaning it is zero displacement, meaning no motion. However, non-zero flat line velocity means something is moving. Right. So, for example, if you drive on a freeway with 60 miles per hour for 3 hours, you didn't change velocity, so you should see a flat line. However, it doesn't mean that you didn't move at all, right? So you drove for 3 hours. Even if the displacement actually changes, if there is no change in velocity, you see a flat line. So non-zero flat velocity means displacement is occurring. If you see a zero flat line in velocity, that means same as flat displacement. There is no motion occurring. Skip into the very last portion, we compare this point and this point. From there is a change in velocity from certain value to 0. So that's how you can interpret the velocity. In summary, when the object or body is moving to the positive direction, velocity is also positive. Also, a flat non-zero velocity is not no velocity. Okay, it only means it is a constant, something is moving at a constant speed. So, as long as the velocity is non-zero flat line, the displacement gives you a linear slope. What happens if we actually do the exact same thing, but now we change just the direction of the displacement? The direction is in the negative direction. Therefore, what you see is actually negative deflection of velocity. But everything else is actually the mirror image of the first example because the only thing that has changed was the direction. So, another learning point about the relationship between displacement and velocity is that when you see velocity that is negative, it doesn't mean something is slowing down or speeding up. So, the sign of velocity doesn't tell you any information about speeding up or slowing down. It only tells you the direction of the velocity. So in the third example from part one, I added some scenarios. On the way, he moved faster, and on the way home, he walked. He moved slower, right? So in this scenario, what happens in the velocity curve? At the very beginning, we have to compare two different points because velocity is by definition difference between 2 points, right? But even though the person is actually moving, when you look at the velocity, it's a flat line. Again, unless it's not zero, it only means something is moving without changing in speed. But the magnitude of speed is much faster, right? Over here compared to the later one when he actually walked slower. So it tells you on the way in the positive direction because the velocity is a positive, then he was moving faster. And once he gets to his office, he stopped. He rested for 10 minutes. That's why you see a zero velocity. And then he begins to move in the negative direction, right? So that's why you see a negative deflection. But on the way back, he was at the constant pace in the negative direction. So that's why velocity is negative and flat non-zero line. One more thing I wanted to mention is that because the change in velocity from here to zero is sharper than this one or this one. So this is the difference between stop, right, to walk or walk to stop. This is the difference between run versus stop. So of course, when you look at the difference, right, change in velocity, the change in velocity between run and stop must be greater than change in velocity between walk and stop, right? That can be evident in the sharper slope in velocity. When you see something switches from positive to negative or negative to positive, that's when you can imagine the moment the displacement changes its direction. So lastly, when displacement actually makes a curved line, what happens to velocity? Actually, you see a straight velocity slope. Now you begin to see an interesting relationship. When you see a non-zero flat velocity, then you will see a linear displacement. When you see a linear velocity, you will see a curved displacement.